Hey, all. This one's going to be a little bit of a vocabulary builder. We've got some new words and actually even a new letter, which is cool. So here we're going to talk about orthonormal bases and orthogonal matrices. So orthonormal bases are actually pretty straightforward. So what we're going to say is we're going to go ahead and we're going to say that, oops, we're going to go ahead and say that a set of vectors v1 on up to vn is orthonormal, and this is going to consist of two words, the ortho bit and the normal bit. So orthonormal if vi dotted with vj is equal to either 0 or 1. So it's 0 if I isn't j. In other words, they're all perpendicular to each other. And it's 1 if I equals j. So that's if I'm dot producting the same, right, the same vector with itself, I'm going to get the magnitude squared of that vector. That vector is going to be a unit vector. Right. So another way of thinking about this is the ortho part means perpendicular and the normal part means unit length. Okay, so that's what an orthonormal set of vectors is. An orthonormal basis is just an orthonormal set of vectors that spans a subspace or a space. Our usual, so this is kind of a note, the usual basis for Rn, right, which consists of like one and then a bunch of zeros and then 0, 1, and then a bunch of zeros. Right? These are kind of the analogy of like the I, J, and K. And then some more vectors, and then you get one that's all zeros except for a 1 at the bottom. Right? This is an orthonormal basis. And the fact that my usual basis is orthonormal and so convenient basically means that I want to label other bases that are that convenient. So this is me giving a word for, hey, this is a hella convenient set of vectors, right? So my new letter is going to be associated to the other thing. So this is going to be my new letter. My new letter is going to be a Q, and Q is going to be used for what we call orthogonal matrices. And an orthogonal matrix, sorry, an orthogonal matrix is one where the columns are, I bet you can't guess. What the hell, Joe? So, we actually define this. So, an orthogonal matrix is a matrix with orthonormal columns. You guys actually know some examples of matrices like this already. I'm sure you've got the first one in your head. The identity is a matrix like this. There's some more. So all the permutation matrices are also orthogonal matrices. And then a couple more. One of the other ones is this R theta matrix that you may recall from one of the exercises. This is this matrix cosine minus sine theta, sorry, cosine theta minus sine theta, and cosine theta. Remember, this is the matrix that rotates space by theta by an angle of theta. Right. So these are kind of convenient matrices. They have some cool properties we're going to spend a second exploring those properties. They're going to be useful. So some of those properties are a property like Q transpose Q is going to be the identity. So this I'm going to make as a claim right now, and we're going to have a quick little proof of this. It's not very hard, right? So my proof is going to be Q transpose is going to have rows that are Qs. So I'm calling all these Qs, and then we're going to have down to Qn here at the bottom. And then I'm going to be multiplying this, and here we're going to have our matrix Q. So this is going to have columns that are these Qs, right? So we're going to have some dots, and then we're going to have Qn here. Looks like I forgot to put vector hats on some stuff. And then if we think about the way this multiplication is going to work, right? When I multiply this vector q, when I pick that up, twist it sideways and drop it on, I'm going to get 1 because q1 dot q1, and then I'm going to get 0, 0, 0, 0, because it's perpendicular to all of those. Then when I look at q2, I'm going to get 0, and then I'm going to get 1, and then I'm going to get a bunch of zeros. When I do Q3, I'm going to get the same thing, right? The only one that's not going to be 0 is Q3 dotted with Q3. So I can see I'm getting the identity matrix out of this. Cool. Great. All right. A cool little like consequence. In math, we call a consequence a corollary. Not sure if you've heard me use that word yet, but it really just means consequence. Like consequence of that, right? So a consequence of that is that if my Q matrix is square, then Q transpose is equal to Q inverse. That's kind of cool, right? So I know that with the identity matrix. With my permutation matrices, that feels a little funny. Remember, I'm not claiming that the matrix itself is its inverse. I'm claiming that if I transpose it, I get the inverse. That's actually cool. If you transpose the R theta matrix, it really just swaps where the minus sign is. One of those matrices rotates everything counterclockwise, and the other one rotates everything clockwise. That's actually really, really cool. So this is a neat little consequence that we kind of get for free. Now, we're going to get something else for free because of this in a second. So let's explore another property. So another little property is this kind of funky thing, like a really, really cool thing. The Q's are length and angle preserving. That seems really wild. So here's the thought. I'm going to look at a Q done to a vector X, and I'm going to dot it with Q done to a different vector Y, right? And then I'm going to say, all right, so that's QX transposed against QY. Remember, this is that cool little fact I've used several times that you can rewrite a dot product as a transpose. Okay, now this is a transpose of a product. So that means it's X times Q transpose times Q times Y. Sorry, X transpose, Q times Y. Q transpose Q is just the identity again. So I got X transpose Y. Well, what's X transpose Y? Well, that's X dotted with Y, right? So essentially, Q preserves dot products, which is cool. So the length part, so the part where I can say that a matrix is length preserving is if I look at the magnitude of QX, right? And I'm going to square this. That's QX dotted with QX. And I just learned that I can basically just pull the Q's out of that. So that's going to be X dotted with X. And x dotted with x is the magnitude of x squared. So I can see that after I did q, the magnitude of x didn't change, essentially, right? Doing q to x doesn't change how long it is. That's cool. The angle preserving is actually just a consequence of two things we've already observed, right? So the angle preserving is that theta is the arc cosine of x dotted with y over the magnitude of x times the magnitude of y, right? Okay, so, well, I know that because of these two facts, I could just snap a bunch of q's in there. That means it's angle preserving. That's really cool, right? If I did like the new theta, right, is the arc cosine of qx dotted with qy over the magnitude of qx times the magnitude of qy. Well, what do I know? Well, I know that I can drop the q's out of the dot product on the top because of this first thing here. And I know I can drop them out of the bottom because of this second length preserving thing. That means the angles have to be the same. Cool. So those are equal. There's no new q. Or sorry, there's no new theta. It's the same theta. That's really neat. I have one more little thing, which is projecting with q's is kind of funny. So if I'm projecting with q's, my projection matrix ought to be q times q transpose q's inverse times q transpose, right? And the really convenient thing here is that this middle bit turns into the identity. And so I get q transpose out of this. Keep in mind that's not necessarily the identity because I don't know how the rows of q interact. But what I do know is I do know that this middle bit drops out. So projecting with an orthogonal matrix is a bit easier than projecting with any old matrix, right? You still need the columns to be linearly independent, but remember they automatically are because they're an orthonormal set, and an orthonormal set of vectors is going to have to be linearly independent. So I think this is good for me, right? These are cool. There's a bunch of cool homework problems involving these. Play with them a bit, get used to them. There's a bunch of facts here to remember, but you guys can do it. So take a second, throw these facts into maybe your flashcards, and then like have some fun with these on homework. They're interesting.